Yes, sir.
Okay,
Good
so
afternoon, all of you, for the seventh session of the ATAL FDP program. Uh, uh, Along with us, our two expert for session 7th is Dr. Sandeep Kumar Shah. He is assistant professor in School of Engineering at the Indian Institute of Technology, Mandi, IIT Mandi. He has obtained his PhD from IIT Delhi and has carried out his postdoctoral research in the University of Saint-George, New Zealand. His research interests include performance-based engineering, earthquake engineering, seismic vibration control, uncertainty modeling in dynamical systems, and design and assessment of structures under multiple hazards. Dr. Shah has published more than 40 research articles in the field of earthquake engineering in the reputed journals as well as in the conference, and also edited two book volumes. He is also a member of several professional organizations like American Society of Civil Engineers, ASCE, Indian Society of Earthquake Technology, Indian Association of Computational Mechanics, and is also currently serving as an associate editor of practice periodicals on structural design and construction by ASCE. I welcome you, sir, on behalf of University Institute of Technology, RGPV Bhopal. Sir is going to deliver the lecture on base isolation for liquid storage tank. Sir, I welcome you, sir.
thank you, madam, for your nice introductions. So, a good afternoon to all the participants. I can see a very good number of enthusiastic participants attending this faculty development program.
Yes, sir. So
And
nearly about 127 participants all over India has registered for this FDP program.
really great, great.
So huge number of participants are interested in earthquake resistant design.
Sure. Okay, so let's see these sessions that I am going to attend. I am going to kindly deliver. We'll be talking about on earthquake analysis or earthquake resistant design of liquid storage tanks. Hopefully, it will be of interest for most of the participants, and we will have some productive discussions during the sessions. So let me present my screen, and meanwhile I'll stop my videos to save the internet bandwidth. My screen visible to all?
Yes, sir. Yes,
Oh,
sir. It
thank
is
you.
audible and visible also. Yes.
Okay, thank you for confirming. Okay, so as Dr. Rawat has already introduced, so I'm not wasting much time on this. So today I'm going to give this talk on base isolation for liquid storage tanks. So why it is important, as we know, liquid storage tanks we can see invariably in different aspects of civil as well as industrial applications. So whenever we talk about water supply, one of the critical component is liquid storage tanks, and to maintain its safety during or post earthquake scenarios also, it has immense role to play for successful post earthquake recovery activities and all those things in civil aspects. Apart from that, liquid storage tanks, as you know, are also kind of a part of integral part of several industries, starting for oil and gas industries, from power generations and aviations, chemical, nuclear power plant, whatnot, and then several many other industries also has liquid storage tanks. For example, the brewery industries, the wineries, they also has a lot of liquid storage tanks, and they need to prevent the content to get damaged during an earthquake. And if you look into the history of liquid earthquake resistant design of liquid storage tanks, These one thing is the nuclear power plant aspect, second is from the oil refineries, and third industry that has contributed a lot was the winery and the brewery industries who actually wants to protect the content during an earthquake, even for minor shakings, because that leads to the quality and all those things. So you might have seen liquid storage tanks in different part of the world in different shapes and different locations. Some of them are cylindrical, some of them are conical, good looking structures. Some of them might be kind of world's tallest tank. Some might be world's largest capacity in terms of volume water storage tanks. Some might be on overhead, some might be on ground whatsoever, and some might be also underground. So specifically the tanks which are placed on ground and placed at some staging, uh, we will discuss about those tanks, how typically the design guidelines are provided for them, and what is the state of art that we can take it forward in the academia. Of the particular structures, but it also can lead to several disastrous consequences. So, for example, if a liquid storage tanks in oil refinery get damaged during an earthquake, there is a high possibility that there will be some fire incidents and those things which may cause severe kind of post-earthquake disasters. The damage to human lives as well as the surrounding structures and other activities that is going on. So you might have seen these pictures during an earthquake for typical liquid storage tanks during the Bhuj earthquake in India. And it is not only in India, it is also observed across the globe, the failure of storage tanks during an earthquake, which caused severe disruptions to the post-earthquake recovery actions. So when we talk about the damages to the earthquakes, there are several types of damages, but some of the critical damages which are associated with the tank wall. It could be in plastic, it could be elastoplastic, or it could be in elastic buckling. Typically, the perfectly plastic bucklings is not kind of allowed in tank designs, as it is an important structure. So we try to keep it in the elastic zones. Nevertheless, it can show elastoplastic buckling, which is typically known as elephant foot buckling, which you can see in this figure. Like this is the elephant foot buckling. It looks like an foot of elephant, so which is occurred due to severe stresses accumulated in the tank wall due to the hydrodynamic forces exerted on the tank wall during an earthquake excitations. There could be sliding of tanks. There could be overturning because of excessive movement due to the lateral horizontal earthquake excitations. And definitely the another option is the tank might be as good as a new after the earthquake, but the failure of the connections, like the pipes that is getting connected to the tank, maybe there are some other equipments, monitoring equipments which are attached to the tank, may get damaged during an earthquake. So overall, the earthquake resistant design of tanks should take care of all those aspects which are necessary to continual function, the functional continuity for an liquid storage tanks. So how a liquid storage tank behaves? So whenever a liquid storage tanks is subjected to an earthquake excitations, so I don't need to give an introductions of earthquake, what is earthquake and how the excitations being exerted on the tank, because I believe all are interested in this domain and has pretty much good background given the course has started since 2 days. So whenever gets whenever earthquake excitation is applied to an earthquake, to a tank, so the liquid content inside the tank kind of starts vibrating. Now, how it vibrates? It vibrates in different ways. If you look at the height wise, the top part of the liquid is almost free to vibrate on its own, and this liquid surface typically shows the sloshing phenomenon. So this part of the liquid, we call it as convective liquid, which can have its own mode of vibration within this few maybe the depth which is from the top, it is not throughout the depth, up to some depth from the free surface it can kind of create an convective motions, and overall it can show some sloshing phenomenon which may lead to damage to the tank wall as well as loss of the liquid if the sufficient freeboard is not available. Whereas the liquid, if you look towards the bottom of the tank, is more or less behaves in tandem with the tank wall. So this part of the liquids are there are different classifications. Some classification says that liquid is divided into three layers. The top is convective, the bottom is impulsive, and there are a layer which is also moves almost along with the tank bottom. So depending on that, these liquids actually try to displace in the horizontal direction when the tank is subjected to horizontal earthquake excitations, and that horizontal displacements exerts lateral forces on the tank wall, which may lead to buckling of the tank wall, or it may lead to the uplifting of the tank base from the support that is in place. So, first of all, to understand the earthquake, the design of, or to go for design of earthquake resistant design of liquid storage tanks, we must look into how we can model it. So there are several approaches to model liquid storage tanks, and with modern computational advancements, even full-fledged modeling in finite element methods of the liquid domain and the tank wall, as well as the soil domain, everything can be modeled. But all those models are pretty much computationally intensive and needs sufficient or prolonged time for performing a single analysis. So there are historically there are several models has been proposed using lumped mass approaches, and one of the model which is typically referred in the research as well as has been used in several design guidelines was proposed by Harun and Hausners. So what they proposed, they divided the liquid column into three layers, and this each layers has been assigned with some mass, stiffness, and damping. So if you look at this figure, the liquid column here in the which is contained within the tank, just for an clarification, this h is actually the height of the liquid column, not the height of the entire tank. So if you look at the modeling idealization of the liquid column, it has been done in three different layers. First is the sloshing mass or the convective mass, then it is the impulsive mass, and the mass which is called as rigid mass, which is moving along with the base of the tank wall. So as I mentioned earlier, the sloshing mass is independent of the tank wall and the tank wall materials. It is dependent on the liquid, more predominantly on the liquid characteristics, what kind of liquid it is. Depending on that, the stiffness is assigned. Whereas for the impulsive mass, as this liquid portion moves in tandem with the tank wall, these properties, the impulsive stiffness and the masses, these are mostly dependent on the tank wall characteristics along with the liquid characteristics. So we need to know what kind of tank wall it is, what is the material properties of the tank wall. then only we can find out these parameters. So these parameters has been proposed by Harun and Hausners, and if you are interested to look into these parameters, the mathematical equations has been given based on the research by Harun and Hausners in several literature as mentioned in these slides. So what you see here, this is a typical idealization of the ground supported tank. Whereas if the tank is supported on some staging, which is known as elevated liquid storage tanks. So in this case, we can safely idealize the structures in two distinct category. One is for the tank structures, another one is for the staging structures. And depending on the staging characteristics, the stiffness and damping of the staging can be calculated, and then the governing differential equations for the equation of for the motions can be derived at. So the equation of motion typically looks like, as you all know, the mass time accelerations into damping time the velocity plus the stiffness time the displacement of each degrees of freedom. And here mass, stiffness, and damping matrices can be obtained and arranged depending on how they looks like, whether it is ground supported or it is supported on staging. Accordingly, these M, C, and K matrices can be formulated. Again, the reference for those matrices can be taken from the literature that I mentioned in the earlier slides. Once you solve this equation of motion using any method of you can use any numerical techniques to solve this dynamic equation of dynamic motions for the tank, you can find out the responses of each of the degrees of freedom. Ideally, there are, if you look at this, there are 1, 2, 3, because these are basically rigid connections. So you have 1 degrees of freedom here, one is here, one is here. So looking at these degrees of freedom, you can solve this acceleration, displacement, and velocity components. And then you find out what is the base shear. Base shear, it is the shear forces, the lateral forces acting at the base level of the tank. And the moment, the overturning moment that is coming, acting at the base of the tank is calculated by multiplying the height parameter here. Similarly, for elevated tank, all these distances will be calculated considering the at the tank base level. The similar things, only the equations will be similar here. Only thing, this UG double dot, because for this case, the MR, the rigid mass of the liquid, is acting in tandem with the ground, so UG double dot was used. However, in this case, this rigid mass of the liquid is subjected to the accelerations which is applied here. This is tower top. This is the staging or tower top of that. There is a node. So this moment and shear can be calculated. So this is kind of a approach which is invariably used in any research works. But again, when it comes to, or if you are performing time history analysis of the liquid storage tanks to obtain the peak responses under earthquake excitations, you can follow this approach. But in design offices, we may not be, we may not have the liberty to perform time history analysis. In that case, we need some code recommendations for other simpler, simplified analysis, which is often recommended in the code provisions in terms of equivalent static method, or sometimes using response spectrum method. So we will discuss here the approach which has been given or recommended in IS 1893 part 2, which is particularly for design of liquid storage tanks. So for the ground supported tanks, the code recommends to idealize the structures into two liquid masses. One is the convective mass, and another one is the rigid mass. So I will spend a little bit more time on this approach because the code recommendations are quite effective for day-to-day design of simple tanks, and we'll focus on two types of tank structures. One is cylindrical or circular in plan, and one is rectangular. So if we look at the modeling aspects, uh, the code has not recommended the rigid portion. Rather, the entire mass has been considered along with the impulsive mass, which is connected to the tank wall rigidly. Nevertheless, this code also talks about some coefficients for design force calculations, which we'll discuss later, for impulsive mode also as well, even it is connected as a rigid body. So the idealization of this model can be done like a single degree of freedom, because it is a nothing but a rigidly connected to the tank. So this sloshing component can be idealized as a single degree of freedom system, and then you have this period of vibrations. So although it doesn't have any stiffness attached to it, but we do have the period of vibrations for both the cases, convective cases as well as impulsive cases. So why it is required, that will come to know at this subsequent slides. So if you look at here, the properties of the idealized model depends on tank wall material property, the tank wall geometry, as well as the liquid property as well. So when it comes about liquid property, there are certain assumptions that it is the liquid we are considering is kind of incompressible, and typically the liquid mass density is used in the equations that has been given. So if you look at here, it has some coefficient Cc or Ci, which can be calculated from the given charts that I will show you later. It also has the tank wall thickness as well as the tank inner diameter of the tank. H is the overall height of the liquid column. So now if you look at this model, if you know these parameters, you can easily find out the period of vibrations of each liquid mass, mc as well as mi. However, if we know mc and kc from other references, we can also calculate the period of convective mode like this, because from the basic dynamics it can be calculated as mc root over of mc by kc. So code recommends you take the minimum of these two values, tc and t1, for calculation of the forces corresponding to the this mass, these degrees of freedom. So it also gives you for the rectangular tank. For rectangular tank, you have L. L is the length of the tank wall, the direction, whatever direction you are, depending on the direction that you are talking about, uh, the earthquake excitation that is going to strike the tank. Accordingly, you have to take the L in the perpendicular direction. And also we don't have an option for like in that case, if it is rectangular, these calculations has to be done, especially the convective calculation has to be done for both the direction independently. When it comes to elevated liquid storage tank, so again, similar modeling approach, but it has been idealized as two stages. One, this ms, mi plus ms. Ms is the corresponding to the mass. Typically, it is taken as 1/3 to half of the mass of the staging, which is lumped at here, and the sloshing mass acting over this, and then staging stiffness is applied here. So this code has recommended we can consider the entire setup as two uncoupled system, one with the impulsive mass along with the staging mass, part of the staging mass. In fact, it is not the entire staging mass, which is attached to the base with Ks, staging stiffness, and the MC, which is attached with Kc. So in the code, there are some corrections that you can I have made, if you have noticed, if some are already are familiar. And then once you have this Mi, Ms, you can find out easily what is the Ti, or the impulsive stiffness, impulsive time period. The sloshing time period is going to be calculated in a similar manner whatever we have done. So if you look at all these idealizations as per the code recommendations, it needs some coefficients to calculate this Mi, Mc, Kc, Hi, Hc. So there are a lot of parameters are there how it can be calculated. So if you look at this figure for circular tank, the code has given you the plots which can be used to calculate the several design parameters of the liquid storage tanks, like that Kc or Mi or Mc, whereas it has been given as a normalized form, Kc in terms of H by mg, or Mi in terms of m, which m is the mass of the liquid storage tanks. Here you can see the variable is given 0 to 1. So as a ratio, you can find out from there. Once you know the what is the slenderness ratio, which is defined in terms of H by D for circular tank, you can find out what is the value of Kc, Mi, or Mc. Similarly, the for the this is actually the height, actually not the mass. So here the height of the different liquid, lumped liquid portion, that convective or impulsive, are given here. Here one thing you can note, there is a star values are there. So what are these star values? Those actually depends on how your tank is kind of connected to the floor, whether there is a base pressure. So I will show you how the base pressure acts in the liquid storage tanks. So if you are considering the base pressure in the tank, then the one values has to be taken. The reason behind this, there could be uplifting of the tank and then behavior of the tank when it has been uplifted from its base, and behavior of the tank when it has not been uplifted from the base because of the pressure at the base. They will have different values of the ideal models. So in that case, depending on that, there are 4 different plots are there: 2 for convective and 2 for impulsive. Similarly, as you have seen, the coefficient for the calculation of time period for impulsive as well as convectives are also given, which can be used. Again, all depends on the slenderness ratio. So whatever the tank dimensions you have, if you can have a slenderness ratio, so ideally it suggests the dynamical systems can be comparable. So whether you have a 10-meter diameter and 2-meter height of liquid in a tank, or you have 20-meter diameter and 4-meter height in the liquid height in the tank, both the systems are dynamically equivalent. So all the parameters which we are calculating are actually plotted in terms of the slenderness ratio H by D only. Similarly, when it comes to the rectangular tank, in this case also, again, all the parameters you look at here, it depends on H by L ratio. L means the length of the tank wall perpendicular the direction that you are considering for your design purpose. So depending on which direction you are taking, you have to calculate the properties in both the directions. And they has to be combined when calculating the design forces. So I was talking about the distribution of pressures. So now you can look at this figure. So this figure shows how the hydrodynamic pressure inside the liquid storage tanks can be represented when it is subjected to an horizontal earthquake shaking. So if you can look at here, the impulsive mass that will typically create a pressure in this mode, whereas the base pressure, you can see it here the base pressure, because of this there will be compression in this direction, tension in this direction, so the base will also be subjected to some pressure. So this is the value it is shown, and because of this consideration of base pressure, you can see the height, the effective height of the impulsive mass has been now changed. So ideally it will act little bit at higher height than from the base than when you are considering no base pressure. So if this tank is anchored in this in its base, there is no uplifting possibility, then probably you will go for this kind of situations. Whereas for the convective mass, again the convective mass, the maximum pressure will be towards the top of the surface of the liquid, and then when you consider the base pressure at the base of the tank, then again the height of the convective mass will be little bit uh, greater than the case when the base pressure is not considered. So this phenomenon has also been simplified in the code. So this code has given some linear distributions of this nonlinear profile, which can be calculated as per the given equations in the code, which will be depending on the dynamic characteristics of the impulsive as well as the convective masses, which I will show you again in subsequent slides. So once you know the pressure, that will lead you to the design of the tank wall. So if we talk about the design of liquid storage tanks, typically four parameters or design quantities are necessary. First, to ascertain the overall stability of the tank, the base shear and base moment needs to be calculated. Our research here has also shown we can correlate this base shear base moment with the tank wall failure as well. But in our case, most of the cases, if we can find out what is the hydrodynamic pressure being exerted on the tank wall, that will also help us to design the tank wall, because the hydrodynamic pressure will subject the tank wall to the stresses in the circumferential, as well as there will be stresses in hoop direction as well. So taking those pressures, you can design suitable reinforcement, or if it is metal structures, the thickness of the tank wall can be designed. Another parameter is also very important, which is sloshing height. So sloshing height means if the tank vibrates during an earthquake, so the how the liquid at the top surface can how much it can displace uh, basically from its original location. So that height is important, because if the height is extremely high in comparison to the available if the height is extremely high as compared to the available freeboard. Freeboard means the tank wall depth with respect to available tank wall above the surface of the free liquid surface. So that if the freeboard is not sufficient and sloshing height is more than that, then there is a chance of liquid loss during an earthquake excitation. Similarly, if the liquid sloshing is too vigorous, in that case, it may hit, in case of a tank which has a roof, it may hit the roof and the roof can get damaged. So if we need to have a good idea about how much sloshing height is expected for a given tank structures, so that we can design the tank roof, or we can design the freeboard with sufficient margin of safety. So here will how we can find out. So definitely all the things boils down to the basic equations that we all know from the earthquake resistant design from IS 1893 part 1. We need to find out the accelerations. So acceleration in the horizontal direction, how it is to be calculated. So again, the formula z by 2 into I by r into sa by z is same as we used for any other structures also. But here, how the calculations are to be done. So Z, it is nothing but this is the horizontal acceleration coefficient. Z is the zone factor. It depends on um, where the tank is located, what is the zone for that particular location. And then I is the importance factor. Again, it is taken as 1.5, or in these revised versions, it has proposed some higher importance factor as well. So depending on how the liquid important it is, whether it is nuclear reactor or it is some inflammable liquids, depending on that we need to assign the importance factor. Then R, again depending on the tank material or the tank, if it is elevated tank, then how the staging is constructed, depending on that the R factor is to be taken. Typically from 2 to 4 is the range for R factor, the response reduction factor. Then SA by G is the spectral accelerations, which depends on the period of vibration. So now AH can be calculated considering the TI and TC, the period of vibration for convective mass and sloshing mass. This SA by G can be calculated. Now once SA by G is calculated for impulsive or convective mass, you can easily find out what will be the shear forces and moment at the base because of the acceleration. So if you look at here, for the impulsive mass, for a ground supported tank, for the impulsive mass AHI, which can be easily calculated from the response spectrum, design response spectrum given in IS 1893, corresponding to the TI. TI can be calculated as shown in the previous slides. Then the mass which is being excited by this spectral accelerations is the impulsive mass, the tank wall, and the tank base, whatever material it is. All the masses will be excited by this excitation. So that is mass time accelerations will give you the design force, the impulsive mass. So this force is known as shear force at the base due to the impulsive component. Similarly, for convective component, as we have already discussed, the convective component is almost free to the tank. It can move on its own. So it only depends on the mass of the convective component of the liquid. The moment, again, the moment can be calculated depending on the at what height the force is applied, the acceleration times the mass, that will be the force, times the height that is acting on, then you can find out the moment. Similarly, same thing is applicable for elevated tank also, but in elevated tank, code suggested that you take the moment corresponding to the case where base pressure is accounted, take those heights and calculate the moment at the tank base. So once you know this VI and VC or MI and MC, then these forces are, if you look at it, ideally they are basically corresponding to one mode, one impulsive mode or sloshing mode or convective mode. They can be combined using any combination rules, but code suggested the square root of sum of the squares. So the code suggests the design forces, the maximum shear force and the moment needs to be calculated by RSS methods, VI square plus VC square root of that sum. Similarly for moment as well. So this can be used for the design value. Now again, for liquid storage tanks of circular plan or the cylindrical tank, these are kind of it doesn't make any difference on the direction of the earthquake excitation. But when it comes to liquid storage tanks with rectangular geometry, then these values again needs to be calculated in both the directions independently and then arrive at the design forces. Similarly, for sloshing height, it can also be calculated using the acceleration coefficients. that that has been computed depending on impulsive mode or the sloshing mode, and it can also be calculated as we are talking about only sloshing mode. So there is nothing like impulsive is coming into only the convective mode. uh, Acceleration coefficients will be required, and then the tank dimensions are present here. For rectangular tank, the length of the tank and the equivalent R value will be there. The response reduction that we are using for the tank, that need to be applied here, because for liquid, response reduction is applicable only for the forces but not for the displacement. Same thing you might also correlate with the drift calculations. When we talk about drifts in the buildings, we do multiply the factor, whatever the drift, elastic drift, by a factor of R. Same thing is happening here as well. So the R factor has been multiplied to get the maximum sloshing height here. So these are, I am not talking about the hydrodynamic pressure here. There are some equations are given in the code, which can be, once you know these coefficients, those equations can be used to get the hydrodynamic pressures, which will lead to the design of the tank wall eventually. So this is the basic background of how liquid storage tanks can be modeled and how.
मैं बोल ही नहीं सकता सर.
Yeah, so I will just take a short kind of discussion sessions. If we have any discussions, you are welcome. So then again, I will go to the next stage of the presentation. Any questions from the participant till now?
Any questions from the participant? Please ask, or you can type it in chat box also. Any questions, please? Okay, sir, you can continue, sir.
Okay, thank you. So any questions you can
You
write
can
on
type
the
in
chat
chat
box.
box also.
Yeah, we'll take that up at the end one by one in that case. So this with this basic background of seismic analysis and design of storage tanks, now we will see how base isolations can be incorporated and how it can benefit in designs. So as of now, what we have seen, the liquid storage tanks are subjected to base shear, moment, and we also need to control the sloshing heights. So how we can reduce them? So as you might already got the introductions about the base isolation techniques, how it helps to minimize the transmission of earthquake forces from the ground to structures, there are various mechanisms. So if you remember the generic shape of a response spectrum of any earthquake excitations, or if you take the design spectrum, it typically looks like this. So after the short period range, if you increase the period of the structure, it is expected to have lesser forces, lesser spectral accelerations that will lead to lesser forces. So what actually base isolation does, it isolates the structure from its base. Now, when I say its base in liquid storage tanks, especially when it comes to elevated liquid storage tanks, it could be either at the base of the staging or it could be at the base of the tank. So in between ground and staging, or it could be in between staging and the tank. So now with that provision of a flexible layer in between the base and the structure, essentially what it does, it shifts the structural period to a higher range. So it elongates the structural time period, a period of vibrations. So it will help to attract the structure in attracting lesser forces. Then another benefit it has, as the structure is flexible at its base, what happens, the structure predominantly shows the mode of vibration which is corresponding to the isolation mode. So because of that, the superstructures behave almost as a linear or sometimes it as acts just like an rigid body. So in that case, what happens? The participation from the higher modes also diminishes. So that also leads to a reduction in the overall forces. And definitely, the base isolation system acts as an additional energy dissipation. It also has some damping characteristics. So that also helps to reduce the force transmissions from the ground to the actual structure. So there are several structure. So there are several kind of isolation systems has been proposed in the literature. Uh, However, traditionally the isolators are categorized kind of it could be elastomeric, it could be late rubber bearing, could be sliding bearing, or it could be roller bearing. So depending on these basics systems, there are many advanced systems has been proposed in recent past. However, the for the discussion purpose, we'll be just showing the modeling approach and how the force reduction is possible in liquid storage tanks that we'll see here. So there are many applications which has been around the year, specifically for the liquefied natural gases, the LNG tanks. They has been isolated using bearings in it is mainly kind of if you look at the European continent, there are several applications can be seen, and you can see that isolators are provided in a kind of a ring manner, and then their tank is founded on this. So you need to develop a tank base here, and then the tank will be constructed. Similarly, it could be raised on some platform, some raised platform, or it could be on the ground itself. So how the modeling change? So I will refer back to the Harun and Hausner's model again for the fixed base tanks. We'll just add the layer, isolation layer in between the tank and the base. So if you look at this, so now earlier the rigid liquid component was connected to the ground. So essentially we are not considering that as an degrees of freedom. But now when base isolator is in place, now this also becomes an degrees of freedom in our case, because there will be a deformation at this location. So now it has 3 degrees of freedom if we consider only one directional earthquake excitation. So if you look at the equation of motions, essentially there will be another component, the restoring force by the isolation system that we are going to use, that is now coming into picture. Also now earlier the equations were completely uncoupled, but when it comes to base isolations, there will be some coupling, because all the above part, this MC, MI, MR, are now connected to the isolation degrees of freedom. So there will be coupling between the isolation degrees of freedom and the other mass, liquid masses, and this F vector will vary depending on how the liquid, how the isolator behaves. So essentially this F term will be different for different types of isolation systems. I am not going to the details of different types of isolation systems, rather I will focus on if the force deformation behavior is different or the modeling approach is different, how it can affect the response calculation as well. So if you look at the matrices and the vectors, you can have this diagram. That is quite self-explanatory. Nevertheless, this F term, if we consider the nonlinear behavior of the term, then you can see there is a hysteretic component, this Zx, Zy, because most of the isolator systems behaves, it possesses an hysteretic behavior, which can be solved using numerical techniques, and then kind of fitted into equations while solving this particular set of equations. So isolator can be modeled in different way. Inherently, kind of all the isolation systems are nonlinear in nature. The level of nonlinearity, it might be negligible, it might be highly nonlinear, depending on different systems. But ideally, the isolation systems, all the isolation systems traditionally can be modeled using this Park-et-al model, uh, where if we consider the bidirectional effect as well in x as well as in y direction, then there will be kind of elastic and hysteretic component which will be coming into pictures, and that can be utilized. So this modeling approaches again, you can see the how these equations can be solved. So these are differential nonlinear differential equations of the first order nonlinear difference equations, which need to be solved using some non-numerical techniques. It is not possible to have an analytical solution of this kind of equations. So using numerical techniques, you can solve the zx, zy and fit into this f equations, and then again that equations can be clubbed with the governing differential equation of the equations of the motion. Then you have an overall solution of the system. So depending on how you are modeling, it can be modeled as nonlinear force deformation behavior. It can be idealized as a bilinear force deformation behavior, where only elastic and an linear but some reduced stiffness in the nonlinear zone is there. It is a linear variation, but it is in the post yield portion. So it is called as bilinear behavior. Then it can also be idealized as a linear behavior for simplifications, because nonlinear behavior, it often gives difficulties in modeling and solving the equations. If you can idealize as a linear model, then the solution of equation doesn't need solving this nonlinear differential equations, first order differential equations. To get directly, we can develop the equation of motions with the help of the effective stiffness and the damping corresponding to this nonlinear behavior. So depending on how you are modeling, so if you look at this figure, it shows the response time histories for moment, sloshing, shear, and the base displacement corresponding to various approaches of modeling. How you are modeling the isolation systems, depending on that, you can see the response, how it is changing. So you look the gray one, it is a response of the fixed base tank where isolation is not provided, and the others, the black and red, they shows the response corresponding to the isolated case. Only difference how they are modeled, whether it is a linear model or it is a bilinear idealizations or it is nonlinear, that I will come to next slide. So depending on that, you can see in all the cases the responses in terms of base shear or the overturning moment at the base, both the cases, they are significantly less than the fixed base cases. So essentially you can say that isolation helps to reduce the response of the liquid storage tanks. Nevertheless, one important observations, the liquid sloshing. As we are making the liquid storage tank more flexible, there is a possibility that the liquid sloshing may get increased, because now it was a flexible structure, flexible part of the tank. Again, we are making the structure, overall structure as flexible. So there could be some resonating phenomenon, or the higher modes, or not higher mode, because it is in terms of the lower mode, the sloshing will be in the first mode or so. So it will be excited when isolation system is in place. So there is a chance that the isolation displacement in sloshing displacement in isolated tanks could be more than the sloshing displacement observed in the fixed base tank. So here you can see the comparison of the responses when with respect to the fixed base, and three different approaches of numerically model the isolation systems for solution of this uh, time history analysis. So you can see for both broad and cylinder tanks, these values for the isolated cases are significantly less apart from the sloshing displacement. And whatever way you model it, the overall response, base shear and movement is expected to be less in all the cases for isolated cases. So further, if you plot the fragility curves, uh, so just to give you a background, fragility curves typically it shows you the probability of failure. You can say it failure, you can say it probability of exceeding a particular damage states with respect to a variation in the intensity measure. So here the intensity measure has been taken as the peak ground acceleration of the earthquake excitations. So if you look at here, so it is not only the peak response for a particular earthquake when you consider a set of earthquake ground motions, and if you consider some random variation of those motions, you can see for all the cases, whether it is cylinder or broad tanks, the probability of failure of the fixed base tank is always higher than the probability of failure of the corresponding cylinder tank in base isolated cases. Similar observation is also there for the broad tanks as well. So these plots are for elevated tanks. So as I was mentioning, for elevated tanks, the isolator model can be placed at the bottom of the tank as well as at the bottom of the staging as well. So wherever you do, the model 1 and model 2 represents those kind of models for isolated tanks. So whatever model you choose, the base isolation system always helps to reduce the probability of failure. So that is one observations which is very, very crucial. And in design of base isolation systems, it can be shown as the beneficial effect whenever you are designing isolation. As your base shear overturning moments are getting reduced, definitely there is a chances of saving monetarily in the design in the terms of material use and all those things. But if you also look at the design life, the chances of failure of substructures will also be reduced. So if you look at the life cycle cost as well as the reliability of the structure, the base isolation system will help a lot to enhance the reliability of the structure, as well as it may help in reduction of cost, especially in terms of material use. You have to keep in mind there will be some associated extra cost at the beginning because isolation system is costly and it may need a specialized designer or experts to design those kind of structures. So initial cost will be a little bit higher. But if you look at considering its lifetime structures, it is possible that base isolation will be much more beneficial in its lifetime. Okay, so given the background of earthquake resistant design and then the base isolation for liquid storage tanks, how it could be beneficial. Now, then another aspects that we need to critically assess is we are comparing these responses mostly for fixed base and the isolation cases. But in reality, if you look at, there is nothing like a fixed base structure. The structure is always going to be founded on soil, and soil is not rigid until unless it is hard rock. So there is a interaction between the soil and structure. So if we consider the interaction between the soil and structure, can this base isolation system be beneficial? So this is the next part of this presentation that I am going to spend some time on the effect of soil structure interactions on the performance of base isolated liquid storage tanks. So what do you mean by soil structure interactions? What happens during an earthquake? How the soil and the structure is going to interact? So that's we are going to discuss. So whenever there is an earthquake shaking, uh, the earthquake doesn't occurs at the surface of the earth. It always occurs at some depth from the surface. So if we consider that is the bedrock level, the some earthquake has occurred. So the earthquake excitations are kind of emerging from this source. What will happen? The seismic waves will travel through the path to the structure, and the structure will be essentially subjected to the earthquake which is reaching that particular site. So now, how we are going to kind of assess those seismic waves, or how those inputs are to be applied in our structure? Because we are not going to measure the building in under real earthquake and going to design. Is not like that. We have to assume the structure, uh, structural model, and take the seismic excitation possible at this location, and then kind of apply that location. But how to get that kind of actual excitation which could be practically applied on the structure? So if you look at the 2 points here, one is free fall when the seismic wave is just reaching, and the other hand when your foundation is placed here. So now when this seismic wave travels, and if you record the seismic wave at this free field, then that is called free field motion. And if you record the same seismic wave when it is interacting with the foundation of a structure, which is denoted here as foundation input motion. So these two motions are not same. So if you record, whenever we get the earthquake recordings from the record database like NGO West or kind of Eurocenter database, or our Indian earthquake database, PACEMOS and all those things. So we typically get the free field motions because those sensors are placed on the free field, and they records whatever the recording is, seismic wave is coming on the surface of the earth. But if we can record the motion at the location of a foundation of a structures, these two motions are going to significantly differ. Why it is going to differ? Because there is an interaction happening between the structure and the seismic waves. So those interactions are known as kinematic interactions, and you have also inertial interaction. So kinematic, inertial, because whenever these seismic waves are touching these foundations, there will be some reflection, and that will inherently vibrate the systems differently. And also, as it has a mass, this foundation will vibrate, and it will also give some inertial force back to the soil. So again, that will also create some motion within the soil underneath the foundation. So those kinematic and inertial interactions will make sure that the free field motion and foundation inputs are not same. So how to tackle this portion? So if we consider this, how we can model this phenomenon. So that particular phenomenon modeling approaches typically comes under this domain of soil structure interactions. So this, as you can show, so this is the free field motions, and here the motions which is disturbed by the presence of the foundations and which is interacting with the foundation. So they are going to be different. How we can model it? So this model can be in two ways. The simplest way is to go for substructure approach. So in substructure approach, what we do, we isolate the problem in two different ways. One is for the ground, one is for the structure. Now this superimposition is done. So definitely whenever there is a non-linearity, then this substructure approach may or may not give you accurate results, because it may it is not possible to ensure that your substructure approach will always be conservative. That we have seen in our analysis as well. So these interactions are typically modeled. So foundations and the structure has been decoupled, and then this we consider under the, this is a massless foundation, that means interaction is not there. It is only we are interacting with the kinematic interactions in occurring, and then you consider the interaction in terms of some springs, lateral as well as rotational springs are attached to it, consider which relates the geometry of the foundations and the soil characteristics. So the equations of this particular spring are provided here, and also the relevant references are there, so those who are interested can dig deep into these aspects. But there is an direct approach which needs the soil to be modeled in finite element based, where the soil seismic wave propagation is modeled within this domain. So we consider the base rock where the actual earthquake ground motion is applied, and then the the ground motion is propagating through the soil domain, and the foundation is attached to the soil domain with suitable connector. No slip condition is provided there. Also the soil domain, it can vertically move, but in horizontal directions all the nodes are typically tied. So the shear waves can propagate in the vertical directions, but there is all the points will move in horizontal direction together. So with this, you apply the boundary absorbing boundary conditions, because the soil domain, if it has finite dimension, then there will be issues of refracting from the boundary. So we need to ensure how long it has to be taken. So for every structure, the domain of the soil in the numerical model plays a crucial role. And also at the boundary of the domain, we need to apply some non-absorbing boundary conditions, so that there is no reflection of the seismic wave, because if some waves are coming, this would not get reflected from here again. This would be escaped the system without changing the interaction between the foundation and the soil domain. So one question comes, when we need to consider the interactions. Do we need to consider soil structure interaction all the time, especially when the base isolation is to be considered? So there are some early studies by Villetsos and Constantino. So they have given some direction in this direction. So if we look at these things, so you can see for a fixed base structures, if this alpha value, which depends on the soil characteristics like shear wave vs shear wave velocity in soil, and the tank dimensions, like if you look at for the tank, then typically H and R, or the slenderness ratios, are related to it. So it has been shown if this alpha value is greater than or equals to 1/8, then the soil structure interaction is important. So that's mean whenever the shear wave velocity is, if you look at here, the plot between this alpha and shear wave velocity, which we had studied, like if it is something in the range of 600 to 650, if it is less than that, then the soil structure interaction is important, because if you can see the alpha value is more than the threshold value of 1/8. But if the shear wave velocity is higher than 650 or so, then we may neglect the soil structure interactions, because the effect will not be much. So typically this region comes under the hard to rocky strata, whereas this comes under kind of loose soil or to medium soil categories in our code provisions. Similarly, if it is base isolated case, in that case also some observations were made earlier. There is a, depending on the slenderness ratio, there is a parameter sigma, and also there is a ratio between the structural frequency and the base isolation frequency. Considering all those aspects, it can be, again, if the shear wave velocity is less than something around 650, 600, almost on the similar range, then the isolated structures need to be considered along with the soil structure interactions. So then only we have to see whether the base isolation is really effective or not. So for this study, we can keep this kind of values as limiting conditions. So considering the site conditions, we may look into the detailed analysis of soil structure interaction consideration or not. So the same model which we had considered earlier with rigid base or fixed base conditions, we are considering with flexible base where soil structure interaction consider. For lumped mass, again, lumped mass approach, again, we are talking about the direct approach will also show, but here we are considering the lumped mass approaches where the soil structure interaction is also lumped using these springs and translation as well as rotational springs are there. So these equations of motion for these tanks can be developed in these fashions. So for reference, you can follow the paper where you can find out the references to these equations of motions. You can look at here. Now as there is a rotational springs, so what will happen? The additional displacement or the rotation of the foundation will create additional motion to the structures, and that rotational motion will give, sometimes we call it rocking motion. This rocking motion will add to this all base shear as well as overturning moment capacity. Okay, so there will be some enhancement. I would not say enhancement, because it depends on whether this UC dot and U theta dot are in the same or opposite sign. Depending on that, it may act in favor or it may act in kind of non-conservative way as well. So the similar approach has been adopted here as well. So under several earthquake ground motions, we have developed the fragility curves for this kind of tanks, both for elevated as well as for the ground supported tanks. And the observations that we made, that for whenever we, and then again the soil categories were also considered, for different soil categories considered. One point I must kind of emphasize here. So what about the lumped mass modeling we are using here? So ideally they were proposed without considering the presence of soil structure interaction. So essentially there is a still need to develop a model which can take care of soil structure interactions, a very efficient or more accurate model for this. But what is our observations with comparison of three-dimensional FE analysis of liquid storage tanks considering soil structure interactions and this lumped mass modeling approaches with soil structure interaction consideration, they do differ if you compare the time histories. But when it comes to the peak responses, the variation is not kind of in the range of 5% to 7%. So for all practical purposes, whenever we are kind of more concerned about the peak responses, especially in the design offices, then these simple models can also be used for this kind of analysis when soil structure interaction needs to be considered. But if you are more focused on the energy dissipations, calculation of energy dissipations, or ascertaining the performance of a particular vibration control measures, then probably you may have to go for detailed modeling, or may have to look for a refined model for the lumped mass modeling approaches, because the inherent assumptions of soil structure interaction not considered has been violated in this case. Although for peak responses, it can be safely considered. Okay, so now if we compare the fragility curves again as developed earlier for different cases, for base isolated as well as fixed base cases, and also considering soil structure interactions or without considering soil structure interactions, these the observations that we had, like whether we consider soil structure interactions or not, the probability of failure for the cylinder tanks are always significantly higher than the broad tanks. So if you talk about the probability of failure, then broad tank is the way to go. The configurations for the broad tank is much more suitable. This also, whenever the intensity is higher, so when earthquake intensity is significantly higher, that is peak ground acceleration is going in the range of kind of one more than 1.2 like that. uh, in that case, what was the observations, that the fixed base tank with rigid base sometime underestimates the probability of failure. uh, you can say it underestimate, or you can is there any question from the audience? Okay. Okay. So what are the observations? If we consider the soil structure interactions, it may happen that the base isolated structures may subject to higher probability of failure when the intensity of earthquake is higher. Nevertheless, at the lower level, the base isolated, if your area is so there was some noise in between, so just sorry for that. So let's so what was your observations? So if any site is expected to have severe earthquake excitations and the intensity peak ground acceleration is expected to kind of cross 1.2 or so, then there will be a questions of isolated base isolated structures until unless we ensure that the foundation is kind of a rocky strata or so, because soil structure interactions for loose or medium loose soils, there is a chances that the isolated structures may lead to higher probability of failure. Okay. And also when it comes to the rocky or hard soils, the soil structure interaction doesn't have much effect. And that is the reason that we have to be very cautious using selection of soil base isolation systems, as well as the preparing the ground for installing the structures. We need to be very, very careful. Okay, so after that, there was a kind of, we also investigated the effect of uncertainties in the soil, because even we describe the soil with its typical characteristics like CRO wave velocity or its density, there is inherent uncertainty in the soil domain as well. And that uncertainty we modeled using a standard probability distributions, and then we tried to capture what is the effect on the overall response, and some interesting results that we had found. In this case, we had as the soil domain, we used the full-fledged modeling. However, for the structural domain, we used lumped mass approach. So overall, the interaction was considered kind of a direct approach that we had assumed, and the soil domain was distributed in different layers with uncertain soil parameters. And then we consider 40 earthquake ground motions, and then a mean value of the excitation was kind of the mean response spectrum. What you can see it here is proven there. The reason, another reason you can look at here, the sum of the excitation has the effect of the kind of has the peaks, the bumps you can see somewhere in the range of isolation period. And also for the liquid, whenever there is a soft soil, there is a chance that your frequency of the structure will be ranging in this range. So there is a chance that amplification of the response might be the cases. So that leads to a kind of uncertain response overall in the liquid storage tanks when there is base isolation is there. So what we did, we chose 40 earthquake excitations, and we tried to minimize the error between the response spectrum coordinates throughout the region, and then we arrived at an average response spectrum, and we choose uh, randomly selected three earthquake excitations, which gives the mean of those three excitations are closely matching with the average of those 40 actually selected suit of ground motions. So we tried now, instead of 40 40 earthquake excitations, we kind of narrowed down to three earthquake excitations which are closely matching to the average of those large suit of ground motions, because running the simulations for this kind of direct approach with 40 earthquake excitations is quite cumbersome. So we have reduced that up to three excitations, and we perform the analysis with these three excitations as mentioned. The details are mentioned here. So what was our interesting observations? We tried to plot the ratio of the sloshing displacements for fixed base case and the base isolated case. So what was observed, that for fixed base cases, which earlier we had seen that typically fixed base sloshing response is less than the base isolated sloshing response. But what we observed when we considered the uncertainty in the soil domains, there were more than 150 simulations were performed with all three earthquake ground motions. And then what was our observations? It is not true that all the times the fixed base tank will have lower sloshing. There is a chances that the base isolations can also have pressures. If you look at here, for this case, when your excitation was intensity was lower, there was only 19% records or simulation shows that the base isolation sloshing response will be more. However, once we start increasing the excitation, the percentage of base isolated case exceeding the sloshing response, then the fixed base case increases. So this was observed for both the cases. So there was no clear trend to say, which is typically earlier it was kind of concluded in many researchers, the base isolation increasing the sloshing response. That trend was actually not observed when we performed the analysis under uncertainty in the dynamic system. Then another interesting found kind of things we observed, the considering the earthquake excitations, we tried to see the amplification factor. So amplification factor we have defined in terms of the input to the model with soil structure interactions and input to the model without soil structure interaction. That's mean essentially you are considering the SSI or not considering the SSI. So how we did, as I explained in the earlier kind of slides, that there could be two different input motions. One is the free field motions and one could be the foundation input motions. So we tried to apply the free field motions separately to the structure, fixed base and base isolated structures, and also we perform the analysis as if the structure and the soil system is connected. So the amplifications has been plotted, and it has been observed like that. Here you can see the kind of impulsive and the sloshing or the isolation frequencies has been plotted here. You can see at some for some of the earthquakes, considering the different levels, the amplification is quite high. It is going more than one when it comes to the isolation period. So whenever the isolation is there, there is a chance that it may lead to amplify the responses. So that is the reasons, whenever for some of the earthquakes it is coming close to one, for some of the earthquake it is coming significantly higher than the one. So there is a chances that the responses during the earthquake excitation for base isolated case, when we consider the uncertainty in the soil parameters, there is a high that isolated case will be excited with higher amount of excitation, ground excitations, and that may lead to kind of enhancement in the response as well. So that is kind of the coverage that I planned for this lecture. So what we discussed in summary, like we have discussed about general approach for seismic analysis of liquid storage tanks, the code specified modeling and analysis procedure for liquid storage tanks, and calculation of the design forces. Then we have also seen the use of base isolations to reduce the earthquake response or control the seismic vibration of liquid storage tanks. And then lastly, we have also discussed about the effect of soil structure interaction on the performance or the response of the liquid storage tanks when it is base isolated or it is fixed base. And what we have kind of, if I give you a generic conclusions, the soil structure interaction is very, very important to be considered for the analysis of liquid storage tanks, until unless the tank is going to be supported or founded in a location where the region is predominantly governed by rocky strata or hard soil. But as you can see, practically the liquid storage tanks, especially the oil refineries and all those parts, are located in the region where the soils are mostly loose or medium soils. So in that case, considering those aspects in the analysis, we have to take the effect of soil structure interactions. And for the base isolation systems, we have to be take an informed decisions whether to use or not to use the isolation systems, considering the structural response along with the soil structure interactions, because there is a possibility, depending on how the intensity measure of the earthquake excitation is expected at a particular site, we need to take a call whether isolation will be a viable solution or not. So that's all from my side. There are some of the selected references that I have used for this particular presentations, which you can check and refer as per your interest. So that's all from my side. Thank you very much. So I leave you with some pictures from IIT Mandi, and if you have any questions, we have sufficient time for discussion now. Thank you once again.
Yes, thank you very much, sir. Like liquid storage tank is one of the important lifeline structure which has to be earthquake resistant. So, sir has explained it very briefly how the modeling is done and how the analysis is done. Any questions from the participants? Please ask. Any questions? You can write in the chat box also. Is any questions, sir? Rajesh Bharti.
So, madam, I can see some chats in the message box. So, if there are any relevant questions, we can discuss.
It is related to your PPT, sir. Any questions, please?
So I will share the PDF version of the PPT with the coordinator. So if it is kind of required to be shared with the participants, the coordinator, Dr. Rawat, can share with the participants if required.
Yes, sir. Sir, one question from my side. The staging height, have you studied it for varying the staging height of the elevated liquid storage tank? Uh,
No, as of now, we have not considered the staging height variations on the response in our studies. We have considered is a constant staging height.
Constant staging.
Yeah,
Okay,
constant.
sir. Okay. But is there the change if the staging height is different?
Okay, so staging height is different. What I can see, like it has a role on the distribution of the pressure because your mass and kind of uh, when whatever you are taking the staging height different, then the shear and moment calculations will also be different because you need to consider the staging height in the where you're looking at, especially for isolation systems, whether the isolator is at the top of the staging or at the bottom of the staging. So that if it is placed at the top of the staging, then my understanding there will not be much difference. But if the isolator we are considering at the bottom of the staging, then the staging height definitely will have significant effect on the performance.
Yes, sir. Yes, sir. Thank you very much, sir. Thank you. Any questions from the participant? You can type in the chat box also. There is one question, sir. How the fixing condition of base and cover slab behavior can be estimated for seismic bouncing?
Seismic bouncing, if it is pertinent to the uplifting of the tank, then probably it needs to taken care how whether you are considering uplifting or not. So if you look at the code, there is a kind of overturning criteria is assigned. So if you are considering that overturning in your model, then accordingly you can estimate the what are the forces you are getting. So if you can fix your kind of you can make your foundation in such a way that it is not exceeding the overturning moment related forces at a particular phase, then that can be called that can be avoided. So inherently that overturning criteria which is given in the code, I have not included the equations here, but it is possible to calculate, and then your foundation can be designed so that it doesn't uplift. If it uplifts, so in that case, the uplift force at the pounding, it needs to be taken care. So that how much it is uplifting, and then how much axial compressive force it will be kind of imparting on the tank wall, that will be very very crucial, and it needs kind of detailed analysis. So you can't get that force directly from the lumped mass model that we are considering. So there are some lumped mass models which talks about this uplifting effect as well. So in that case, you need to define the kind of stiffness and damp and dash spots at the periphery of the tank as well, and then that forces coming onto those stiffness, it is possible to estimate the forces. And you have to make sure that forces, whatever the force is transferring at those degrees of freedoms, are kind of can be taken safely by the tank wall as well as the foundation. So for this model, that uplifting force directly, it is not possible to calculate. You can calculate from the overturning criteria only.
Yes, sir. Thank you very much. There is one more question. Is there any special consideration for?
Madam, I think mute. Your mic is probably muted.
Okay. Is there any special consideration for loads? Something like that.
Loads means
Some
Mr. Rao. Loads. What do you mean by loads? I was not clear actually. Special consideration. So, if you sir, please explain what do you mean by load considerations. So, definitely the loads in the term of your typical dead load, uh, wind load. If it is elevated tank, it is very important even in ground supported tanks or as well. Those are there. Apart from this hydrodynamic pressure calculation, that is very very important for design of the uh, tank wall especially. And then for shear force moment, we have considered here from the seismic point of view. But apart from that, from dead load analysis and wind load analysis, whatever the forces you are getting, that you need to consider.
Yes, sir. Yes. Any other question, please? Rajesh Bharti, any question, please? So, if no questions, sir, thank you very much for your session and elaborating in detail the okay base isolation system used for the liquid storage tank. Thank you very much, sir, for sparing your valuable time for
Thank you,
our
madam,
ATAL FDP
for
program
inviting.
participants. Thank you very much.
Thank you all the participants for your patience during the sessions.
Thank you, sir. Thank you.
Nice interactions. Thank you.
Thank you, sir.
Thank you, sir. Thank you. So, participants, please mark your attendance for this session. The link is there in the chat box, and we will again join at 3 p.m. We will have a lunch break. Thank you very much.
Yeah, thank you, ma'am.
Thank you.